Venus and Mercury are the planets that will always be close to the sun. Venus is kind of a morning star. It's a morning object right now, I think. Question 11, which of the following is the best sentence? Earthshine, the best answer is C. It's that kind of ghosty looking thing on the otherwise non-illuminated part of the moon because of backscattering from the sunlight on the Earth back to the moon. So D is the best answer there. 12, Jovian planets, what do they have in common? And so B, all the Jovian planets, remember Jovian planets are Jupiter, Saturn, Uranus, and Neptune. They all have moons, they all have rings, and they all look like they swallowed a terrestrial planet. So they have a rocky core. Question 13, which of the planets does it have that like crazy sort of tilted axis of rotation? And the answer there is Uranus. And actually and I don't have it here to show you, but when we're looking at the images of the planets, Uranus was the one that looked like it had been fallen down. So, bless you. Thank you. 14, which of the Galilean moons? You're looking at Io, Europa, Ganymede, and Callisto. That was probably a little harder one. Which of the following is not a type of galaxy presented in lecture? And A is not. So we have spirals, barred spirals, and ellipticals, but Bode's galaxy is actually a galaxy with that proper name. Question 16, of these scientists, which of them actually still was with the geocentric model? That would be C, Ptolemy. Question 17, if you are out in the course of the single evening, how will the stars move? And the answer is C, that they will move counterclockwise around Polaris. The first part of that might have thrown you off, but I didn't mean it to. They'll stay a rigid pattern, but they'll move counterclockwise around Polaris. 18, which lists the planets in orbits from closest to the sun outward? So that's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. My very educated mother just served us, and it used to be 9 pizza pies when we had Pluto, but now it's just served us nothing. So I don't know. 19, which of the following statements is not true? And so A, it's not true that the winter solstice in the northern hemisphere occurs on or about January 15th. Instead of it's a month before that. It's December 21st to 23rd or so. The others are true. Question 20, where does nuclear fusion occur in all stars, including our sun? And that's C, the core. 21, where are comets in our solar system located? The Kuiper belt is like in the plane of the ecliptic, but outside Pluto is kind of a Kuiper belt, beginning of the Kuiper belt. So they're out there, either that or the Oort cloud. And I didn't have Oort cloud up here, so it has to be where it's cold, right? Question 22, observational evidence shows that our universe is about 13.7, 13.6 billion years old. Question 23, in our culture, we divide the sky up into 88 non-equal regions, and make constellations out of them. 24, which planet is known for the thick clouds of sulfuric acid? That would be Venus, A. Question 25, which of these is not true about eclipses? B, it's not true to say that the moon must be in its new phase for a lunar eclipse to occur, because it needs to be in its full phase to get a lunar eclipse. Question 26, which lists the formation of our solar system, the terms associated with the formation of our solar system in order of the correct order. So it starts out as a solar nebula, began contracting, and we made those cute little planetismals, and then the protoplanet, and then the sun began nuclear fusion. So A is the best answer for that. Question 27, thank you, Hannah, who pointed out that I actually had, for all of these, I had, was it waning crescent twice? So I gave you extra credit, but I told you to fix it, you should take the first waning crescent, which I'll go right down to I really had intended D to be correct. If you take the first waning crescent and make it waning gibbous, then actually that makes D correct. So extra credit there. Question 28, our north axis of rotation right now points towards the star called Polaris, C. A neutron star in 29 is formed. The best answer there is B, after a star explodes and its core collapses to make neutron soup. 30, which of the following objects is most responsible for the Earth's tides? And the answer there is C, the moon. gravity thing. 31, where would you find Ceres? It actually is a dwarf planet located in B, the asteroid belt. Question 30, I was after parallax. As things change, as the observer changes its position, things that's nearby will change its relative position against the background as the observer moves. 33, the average distance between the Earth and the Sun is an astronomical unit, or AU. 34, I was after plane of the ecliptic. I think if you put the ellipse, I either gave you full or part credit. It wasn't a very good question because according to Kepler's first law, the planets orbit the sun in a shape called the ellipse, called an ellipse. So, question 35 was a meteor shower. When we have, when the Earth passes through comet debris, that gives us potentially a nice show, as long as the moon's not too bright and making it hard to see those streaks. Question 36, a giant molecular cloud is that big old giant molecular cloud where a bunch of stars can be born at the same time. 37, regolith is that gray powdery stuff on the moon. 38, planetary nebula was what I was after. If you just put nebula, I think I gave you 1 point out of 2. But planetary nebula is that kind of that cool looking thing where there's probably a retiring star, if not already retiring, kind of it's got material kind of shuffling off. Mare, that's not more, it's Mare, are those dark regions on the moon. Highlands are the light regions. 40, solar wind is kind of the blowing from the wind in all directions. 41, a spring tide is when the tides are created by the moon, and spring tides occur when the sun gets involved and kind of works with the moon. And that happens either at new or full moon. Question 42, I was after black hole when matter is squished or compacted to the point where that folds the fabric of space and time in on itself. Question 43, I was after celestial spheres, kind of you have the Earth there and kind of this kind of ghosty looking sphere outside the Earth. We call that the celestial sphere. And then these you needed to answer 6, so 3 you could kind of not do. The first one is the layers of the sun. So the inner are the radiative, convective, inner is the core, radiative and convective, and then the outer is the photosphere, chromosphere, and corona. 45, might have had one person do 45, but 45 was probably the most maybe difficult, was where Hertzsprung-Russell diagram, you kind of show the stars in different stages of their life. So we have main sequence stars, giants or supergiants, and then white dwarfs. The next one, 46, I wanted you to somehow kind of use these terms to describe a crater. The central peak is the belly button of the crater, and then sometimes we have these terraced kind of walls, and the ejecta blanket kind of goes out. The next one, I was looking for these lines of latitude. So at 90 degrees, you're looking at the poles. So we have North Pole, South Pole. And then at 66.5, and you're looking at the circles. So we have Arctic Circle and Antarctic Circle. And then at 23.5, you're looking at the tropics. We have Tropic of Cancer, Tropic of Capricorn. And then at 0, you're at the equator. And the last page, and I don't have, like I said, I don't have this here to kind of pull up for you. But here they were. Then this one, to go ahead and give me the 3 M's, meteoroid, a meteor, and a meteorite. And I kind of think of them in that sense because a meteoroid is a rock outside the Earth's atmosphere, a meteor is a streak, and meteorite is what you can pick up. And for 50, I was after kind of some information about the Milky Way galaxy. I have the kind of 4 major spiral arms, black hole in the center, it's called Sagittarius A star. Our solar system is kind of halfway between the center and the outside. So if this is 100,000 light years side to side, that puts this at about 26,000 light years. Thickness, you're looking at about 2,000 light years. Thick, not thick. And then the next one was Kepler's 3 laws of how the planets move. First law is the shape, it's an ellipse. The second law is that it moves fastest at perihelion and slowest when it's farther from the sun at what we call aphelion. Third law is that like the order of the planets when they're farther from the sun, they just move more slowly in their orbits. So Jupiter moves more slowly than Mercury. And then the last one was to tell me the solstices, and what I was looking for is the month, and you can see I just totally bail on the whole thing. I go 20, and sometimes it's maybe as early as the 20th, 21st to the 23rd in the month of June, summer solstice. In the month of December, winter solstice. Then we have our fall equinox in September and our spring equinox in March. So there's that. And then remember that the final exam, which will be here before we know it, I kind of take it easy on myself, and I basically look at your old unit exams, and I pull questions, some of my favorites, hopefully the ones that people got right, and I put them on a final exam. And I make a review video for that too. Like I make a review video for the unit exams. And it's going to go something like this, where I basically pull up the old unit exams and I put an X next to ones that will not make it. So I kind of just whittle down so you guys don't have to study so much. Okay. So I'm trying to think, see if we're going to pick up where we left off with fronts and air masses. So I won't make you come to the window, but what do you think about these? What do you think about these here clouds? Do you think they're very high up, or you think that they're kind of middle clouds, or you think that they're low clouds? You can go to one if you want. It just looks kind of gray. What's that? I think they're kind of lowish or middle. Lowish or middle. They're not high. I've seen high clouds before. So if they're low, then they don't have a prefix alpha or cirrus. Are they raining? Is it precipitating? No. So we're not going to talk about nimbo or nimbus or anything like that. Are they flat or fluffy? What's that? They're kind of fluffy? They're kind of maybe fluffy on top. I think to me they look kind of flat. But
I can't see them. So
yeah. How many people think they're kind of fluffy-ish? Because they do seem kind of fluffy-ish. How many people are kind of flattish? Yeah. They could go either way. In fact, that brings up the good point. When we talked about star types, oh my goodness, we talked about cloud types. There's, I'll put L for low, M for middle, H for high, and we're kind of thinking here-ish, okay? And it could actually be kind of it could be kind of doing that sort of thing, kind of connected together. So they have a little bit of fluff. So I'm looking at either stratus, which would be totally flat, or I'm going to look at cumulostratus. See, the cumulostratus, that's a cloud. A cumulostratus means that it's a relatively low cloud and it's got some fluffiness and some flatness to it. I'm looking at either one of those. But we're not going to use a nimbo because it's not precipitating yet. Now let's the other thing I wanted to bring up. So some of you might have seen I was kind of trying to find a few things on the... Have you ever heard people say that they get aches and pains when there's a weather system coming through? Yeah. We'll talk more about that maybe a little bit today, but more about it on for sure on Monday. But it's called the pressure. It's called the barometric pressure. And this thing, anybody have one of these at their grandparents' house? Okay. Well, I haven't had one of these on my wall, but I did when they were going through my in-law stuff. When I saw this, I did not have to take it. So it's a more old person thing. But what happens is, and I'm going to kind of squeeze a little bit. If I squeeze it, what happens to the dial? It moves up a little bit. So it's supposed to go up. And if it goes up, what's this word over here? Yeah. Okay. And if it goes down, if the pressure goes down, what's that word over there? Yeah, rain. So we have this sort of, and actually we've got one in our kitchen that has a little icon. Is it going to rain? Or is it going to be clear skies? And all it's doing is looking at the pressure. So, yep, low pressure, rain. high pressure, fair. That fair means clear, okay? So rain. So we have this, and sometimes in meteorology it's called tendency. If you hear people meteorologists getting all excited, they'll say, ooh, the pressure is dropping, okay? And actually that's an indication that something's happening. It's funny because it's almost backwards, because I'm like, high pressure. Well, if you look outside, you're like, you know, all those clouds kind of make you feel a little claustrophobic. To me, I like the sun. I think most of us do. So when you see the clouds, you're like, oh man, I feel the pressure on me. But honestly, clouds means falling pressure. So that's one of the things you know, flip in your mind. So today, this is kind of, I've got a few weather sites pulled up. So those colors go along with blizzard warning. Are you serious? Okay, so the blue means winter weather advisory. So this kind of leads into, I'll look at IntelliCast. This is the surface map, and we're going to be picking up where we left off. So what's this blue line up here? The cold front, perfect. And then what's this red line? Warm front, yep. And what's this alternating? See if we have, yeah, here's a good example. Over here in the west, what's this alternating? Starts with letter S. Yep, stationary front. Yep, so we have a stationary front there. Kind of a little bit of a stationary front here. And we are right there. Like, oh, direct. So we had a nice day yesterday. One of the things that can happen along these cold fronts or warm fronts or even stationary fronts to a lesser extent is you can have uplifting, and anytime you get uplifting, you can get clouds to form. And if you get clouds to form, there's enough water in those clouds, and there are clouds, it's going to go ahead and precipitate either snow or rain. All right, so where we left off, I think we did this slide. Does that seem right? Mm-hmm. Okay, I thought so too. I think I have another copy. And we're ready for this slide? Or do we do this slide too? Mm-hmm. Okay. All right. So you guys told me that warm air rises and cold air sinks, right? So this actually, I have a couple of figures to show you. This, we've talked about air masses, right? And here we have a cold air mass and cold air sinks. And we have a warm air mass in front of it, and the warm air is going to be pushed up. Now this actually slope is usually pretty abrupt for a cold front. I know this is a cold front and not a warm front, even though we have both a cold and a warm air mass, because the cold air is being aggressive. If it was the warm air being aggressive, it'd be a warm front. The CU, if you go back a few slides, stands for cumulus clouds, and the AC stands for altocumulus. So we kind of have these clouds being formed right at what we call the transition line between the cold air and the warm air. Now this is kind of the opposite of that. The title of this is a warm front. So in this case, we have warm air being the aggressor, but here's the deal. The cold air, it's kind of marching in on, is stubborn. It's sinking there. It's like, hey dude, I was here first. And so the warm air then, all it can do, it can't really push the cold air out of the way as scrape it off of the ground as much as a cold air mass, but it goes up and over. And actually, we call that overrunning. So this right here is called overrunning. So you have an abrupt transition zone with a cold front, and you have a nice slopey transition zone with a warm front. So overrunning is this right here. See, is that the chemical slide? I'm going to add to this a little bit. So this right here, situation, this is where you are going to have possibly storms. And you're going to have, if you think back to your springtime or your summertime storms, you're going to have, I put PPT for precipitation, if that's okay with you. Precipitation will be short-lived. Short-lived, but it will be intense. And if we compare that precipitation event to this precipitation event over here, this you're going to have no storms. And instead of your PPT, which stands for precipitation, will be long, last a long time. And the other thing is it won't be intense. Now, that's a very broad statement, but it's, broadly speaking, the truth. But for both of these, and again, we're going to kind of, I don't know how much we'll talk on it, but when we talk about pressure, for both of these, when they start coming, you're going to see the pressure falling. If it falls quickly, you probably have a cold front coming through. If it falls kind of slowly, you probably have a warm front coming through. And it's funny, all sorts of things with the pressure drop. And like my ears are kind of popping, your ears might pop. You get aches and pains and that sort of thing. Animals know it's coming. You know, our dog does not like storms, and they feel that barometric pressure, that pressure drop. Okay, so we had a cold front, a warm front, a stationary front, and the last one was this thing called an occluded front. And my favorite thing about an occluded front or whatever, I think of it as not 2 air masses, but 3 air masses. So at the crux of an occluded front is that the cold air is more dense. Not only that, but cold air can outrun warm air. That's it. So basically, if that cold air outruns the warm air, and again, it hugs the ground and kind of scoops up and moves the warm air up, it moves the warm air up and over, and it basically catches up with the cold air in front of it. That's an occluded front. Okay? So at the point we call occlusion, that kind of warm air between the aggressive cold front and the cold air in front of the warm front it's replacing is lifted up. So they have 3 air masses. And again, we kind of talked about CP. What does CP stand for? You guys remember? C stands for, is it continental maritime? Yep, polar, yep. Continental polar, perfect. What does MP stand for? Maritime polar. Yeah, very good. So we have two cold air masses, because that's what the P means, but we have a dry one and a moist one. And it's picking up some warm air, and that warm air must be moist because it looks like we're getting a little bit of a thunderstorm cloud there. I know it's a thunderstorm cloud because it has a lot of what we say vertical development. Remember, thunderstorm clouds are ones that basically go low, middle, high, right? In fact, they go so high when we start to talk about thunderstorm clouds, they basically, and you kind of see this one, they flatten out at the top of our troposphere. You can kind of see, we call that an anvil. Let's see this anvil here. So this is just kind of a slight variation on occluded front. All right, so I think this is a figure from your textbook that kind of shows you just a snapshot. It's not colored the right color, it's not blue, but how do we know this is a cold front? 2 ways actually. Triangle. Triangles, yep, and the fact that it's coming from the north. Both of those, yep, cold front. Cool. A lot of times, and they call these kind of station models, you'll have, for instance, Denver has 2 temperatures. 45 is the temperature it is, and 20 is the temperature you need to cool it down in order for dew or condensation to occur. It's called the dew point temperature. So the closer the actual, see San Francisco, the closer the actual temperature is, 54 Fahrenheit to 43 Fahrenheit, means that it's closer to the dew point. It means that if we were to calculate the relative humidity, it would be higher. So that's kind of how that works. All right. So this is an assignment, actually, it feels like the first one, the water cycle, and I didn't double check, but the water cycle one seems like part one. And then the air masses and air fronts seems like part two. So, bless you. Thank you. So this will be due on Monday when we meet. Okay? All right. So let's take a look at the next part. Yeah, we're going up to Iowa State tonight, and our daughter, she's a freshman up there, so she's like, y'all come get my refrigerator, my microwave, and all that, because I'm ready to come home in a week. Their finals are like earlier than ours, so I don't know. I'm like, okay. But we get the weather. It's not going to be a very good weekend to move. Isn't this gorgeous? Here's the sliver of a moon. And since the sliver is on the left, it must be a waning moon. Actually, this morning, the last couple of mornings, the moon's been like that. So what you're looking at, I think this is right. No, it's right. We're trying to get a sense for the Earth's atmosphere. So the Earth's atmosphere is held in place by gravity. I bet you're probably good with that. As we walk around this room, and we're going to talk more about it, most of the gas particles we bump into are nitrogen, and it's like 80-20. So 80 nitrogen, about 20 oxygen, and then some other miscellaneous stuff. So this is a photograph taken from probably International Space Station, and so here's the Earth, and you kind of get a sense for how thick the atmosphere is. So if the Earth's diameter is about 8,000 miles, how many miles do you think this is? You guys are good at guessing. I guess all the time. No, it won't. Write it down. Everybody write down. How many miles? How many miles do you think it is there? It's like the jelly bean thing. Jelly bean thing. So just go ahead and put it right here. Oh, yeah. Oh, yeah, there. Okay. Oh, some of you guys were close. 60.
I told you I'm not good.
I think if I took the average of you guys, it would have been about 60. But do you think that, like, as we we're on the Earth and we go up, do you think that it's like the same all the way throughout? Like, if we climb a mountain, is that air up there the same as this air? No. So what is the word here? What's the most abundant gas, did I say? Nitrogen. Very good. And this is kind of how it's broken up. I said 80-20. This is 78-21. What's the third most abundant gas? I'm thinking argon. Yeah, and then carbon dioxide. Yep. So aerosols, you might not be, like aerosols are like hairspray, like an aerosol. Sometimes deodorants are aerosols. Okay, if you think of an aerosol, basically you have some sort of propellant, which is not CFCs anymore, some sort of propellant that sprays a mist. That's an aerosol. So we have aerosols in the atmosphere. And it kind of, there's a new study out that they're talking about, boy, you better close that toilet lid, because anyway, that's kind of thinking aerosols, but anyway, we have what was I going to say? Oh yeah, walking around, we are bumping into liquid particles and solid particles. Those are aerosols.
Why should we close the toilet?
What's that?
Why should we close our toilet?
There's like a new study, and it's about, and I usually don't do much mind about it, but just the action of the toilet, it puts spray out. And so, like, they were just terrible, but it aerosolizes like poo, like fecal matter. And then you go to the point where, like, if you go to a public bathroom, they don't have toilet lids. So what are we gonna do? Okay. So anyway, I know that, but aerosols, these aerosols are okay. So anyway. So I'm going to underline the word permanent because we're going to talk about two different gases. Now, these aren't aerosols. But the word permanent means always there. Okay? So they're relatively constant. So this list over here are permanent gases. Not so surprising. We have nitrogen, oxygen, argon. Those were the three most. But I don't see carbon dioxide. Right? That was the third most abundant gas. That's because carbon dioxide is a variable gas. And I'm going to underline the word variable. So this is the variable gases. These are the permanent gases. So variable gases means they vary in two ways. And I think it's on the slide. They vary by location and they vary by amount. Very location and time. I think this probably should be location and amount. I'm liking that better. AMT for amount, that's okay. So, well, time, I guess. Yeah, they vary by time. I guess three things: location, time, and amount. But anyway, so water vapor can vary from 0 to 4%. So yesterday in lab, we came up with 46-ish% relative humidity. If we were to go check it today, it might even be higher. Okay. So that's the water vapor. When we check humidity, we're checking water vapor. Carbon dioxide, and I'm going to show you a graph of carbon dioxide in the atmosphere. Carbon dioxide varies with the seasons, and it also varies from year to year. So with carbon dioxide, what I want to try to kind of show you is two major trends with carbon dioxide and variable gas. Another, or the third main variable gas is ozone. Ozone. So probably at this point in kind of the material, you want to know the formula for ozone is what? O3, chemical formula for ozone, you got it. So ozone, now you don't know this word yet, but I think I'm gonna go ahead and put it on the board. Stratosphere is a layer of the atmosphere. So it goes like this. If this is the Earth's surface, it's, let's see, 4 layers, and I'm going to kind of show you, relatively speaking, this first layer is pretty thin, and then it gets thicker and thicker. Probably even more exaggerated than that. This first layer is called the troposphere. And the second layer is the stratosphere. And within the stratosphere is the ozone layer. You've probably heard about that before, and it's within the stratosphere. And then we use the word meso for middle. Then we have the mesosphere, and then we have the thermosphere. At some point, you figure we're actually leaving the Earth, we're leaving the influence of the Earth's gravity. So we say the thermosphere kind of just peters out into outer space. Beyond that, we have outer space. So those are the layers. So the good ozone is in the stratosphere. Okay. So one of the things that I would cover in astronomy, and I want to definitely, or the study of our weather, is this idea of how the Earth's atmosphere can give us blue skies. If we were on the moon, okay, in the daytime on the moon, it's just crazy. And I think I've seen pictures like this. So here's the kind of the regolith gray moon. We have a little man standing on here taking a picture. It's daytime. he, because we never had any women on the moon, I don't think yet, can see the sun over there, but it's black all around him. It's black skies. The moon doesn't have any atmosphere to make the skies blue. So the way the Earth makes the skies blue basically is, this is the Earth. Of course, if it's sunny day, we go out and we see the sun, and we see kind of blue all around the sun. So what's happening is sunlight from the sun is coming through the Earth's atmosphere, and the blue actually is kind of ping pong. The blue color from the sun is ping ponging around and it's what we call scattering and making our blue sky blue. That's it. And then at nighttime, of course, we don't have the sun sending us all that light to be ping ponging around. We have stars sending us light, but it's not the same thing as the sun sending us light. So that's called Rayleigh scattering. And the thing that does the ping ponging around, what does N stand for? N2. Nitrogen, yep, and what's O2 stand for? Oxygen, yeah. And I know the two thing might throw you off a little bit, but they are what we call diatomic elements. That I might have, when we talked in chemistry, did the Hoffer nickel. Okay, those are diatomic elements. So the word there is scatter. They have scatter. When in doubt, when talking about why your skies are blue, look for the word scatter. So they scatter a component of light. So do you guys remember the mnemonic device? I'll start you out. Starts with red. Red is the longest, and violet is the shortest. What's between them? Do you remember? Yep. So I heard you say, and the first name? Roy. G. Yep, Biv. Perfect. So I'll go ahead and put long, and the symbol for what's long is this. This means wavelength. It's kind of that upside down V with the tail. We've talked about electromagnetic radiation and wavelengths, and this has a short wavelength. Perfect. Roy G. Biv. And as it turns out, the scattering is selected for the short colors. So it's this blue, indigo, violet that gets scattered. The name for the scattering actually is in the top of the slide. It's called Rayleigh scattering. It must have been Rayleigh scattering. It must have been Professor Rayleigh. Okay. So blue is the word there for the third bullet. So that's why the Earth's sky appears blue during the day. And you can kind of see the ping-pongy bit. So here we have the sun high in the sky, and it's sending us Roy G. Biv, and the Biv is getting scattered. Well, actually then, and actually on the next slide talks about this a little bit. So before I go to the next slide, let me tell you something you already know. When the sun is low on the horizon, this could be sunrise or sunset, then it doesn't, it kind of has, this whole sky has an orangish cast. Okay, an orangish cast. And the reason for it is that when it's low, it goes through more of the Earth's atmosphere. So you have ping pong, ping pong, ping pong, ping pong, and basically you run out of blue, indigo, and violet. So what gets to you are those longer wavelengths that aren't scattered. Well, there's all sorts of wonderful things that happen in the summertime. One of them is like if you're driving down the road, it doesn't even have to be the crack of dawn, but if you look at the sun's low on the horizon, sunrise or whatever, if you look at a speed limit sign, I mean, it just glows orange. It's just gorgeous. And that's because that's the only color that makes it through. So that's what this is talking about. It's the same scattering is also why sunrises and sunsets are so colorful. What do you think the word there is? When the sun is blank on the horizon at either sunrise or sunset, what do you think? 3 letters. Low. Yep. sun's low on the horizon, this can happen. What do you think that word is? The blue light component from the sun is blank so much that the visible light reaching the earth starts with letter S. Yep, very good. Scattered, scatters. You got it. I should have you guys write the test. So, the next word is dust. Aerosols and dust particles actually can enhance this sort of scattering. So a few things come to mind. One is during harvest time around here, we get the dust, the farmers do their thing, and we get a little bit of extra dust, or I don't know if so much in the springtime because there's moisture to kind of keep the dust down. But we can have some gorgeous sunrises and sunsets, and it's actually that particulate matter that's enhancing that. The other thing, oh my gosh, is, here's my map of the United States, and over here in the West Coast, they've had some forest fires. Actually, in Canada, they've had some forest fires. And as the dust from those forest fires gets in the atmosphere, sometimes it finds its way to the Midwest. We have had some awesome, some strange visible effects because of that particulate matter. For instance, the moon, we've had full moons that were like real high in the sky and they had this orangish cast to them. It's maybe been a couple summers ago. But that's because of the particulate matter that's coming and scattering the light from the moon and preferentially just allowing the long wavelengths to come through. So cool. And not as long as that, maybe a year ago or so, and again, it had to do with forest fires. You would get up and there'd be no clouds in the sky, and yet all day long you'd have this like orangish glow. Again, it's particulate matter. So that's interesting. Variable gases, I said there were three: water vapor, carbon dioxide, and I said the third one was ozone, was a variable gas. So I said the ozone actually varies in two ways, and hopefully you can kind of see the two ways here. This looks like a really noisy curve. Noisy means it looks noisy, but it looks like it's kind of cyclical. So each bump represents a different year. This is the year 1960 to the year 2015. So the way it works is carbon dioxide, and make sure I get this right. We'll go through here and make sure I get it right. Carbon dioxide every year is affected by plants. And here's where, I'll kind of butch this. This is my leaf up here. Here's my plant. One of the things about all things that are green is during photosynthesis, the plant will take in carbon dioxide, CO2 gas, and it will spit back O2 gas. And actually, it's photosynthesis, or plants doing that thing, that very thing, that is how we got our 20% oxygen in our atmosphere. It's amazing. It was actually marine algae. So it's a wonderful story. So bottom line is the reason we kind of see these bumps go up and down each year is about springtime, the plants start doing their thing. And what the plants are going to do are actually going to take in carbon dioxide. So that's going to be a dip. But there's a delay in the dip. It's not until about August or September that we have our, I'll put these, so I said spring, peak, CO2, and fall, I said minimal CO2. So about springtime, you figure plants have been on vacation, all winter long, and that's when you're going to have your maximum CO2. And then about fall time, they've been doing their thing all summertime, and that's where you're going to have your minimum CO2. So that's how that goes. There's also a year-to-year trend here. And so you can kind of see the up. It was about, it's been 2-3 years ago when, and not a good thing, it was all in the news that we finally crossed the 400 parts per million Yeah, with an M, not a V, parts per million CO2 in our atmosphere. Okay. Let me show you right quick the latest data. So of course, and it's sad face because this trend from year to year is has nothing to do with plants. It has to do with human activity, specifically using fossil fuels. Okay, so yeah, we're at 410, which is not necessarily a good thing right now. I'm going to show, that's the CO2 right now. You really can't get it. This is, how about this is 1 year? That works. So you can kind of see the autumnal minimum. And then there's one more I want to show you. Now you're going to be like, CO2, how do you get CO2 back 800,000 years? And the answer is a variety of ways, but the biggest answer is trapped in ice cores. Like, have you ever seen the movie The Day After Tomorrow? Its opening scenes is these people are out getting ice cores where they drill down and get this ice that's been undisturbed for hundreds of thousands of years. So there's the CO2 concentration going up. Now get your bearings, because that's 800,000 years ago. The concern is, and actually you can see that it peaked out at, I'm looking maybe 300 parts per million. But this part right here, this is like when the Industrial Revolution kicked off. And this right here is what we're concerned about, the 300 to 400 parts per million. So anyway, that's the CO2 from year to year. That's a good place to stop. I know we're stopping on a sad note, but heard on the news the other day, it'll be okay. Oh, sorry, the word is rise. Yeah, you probably figure out that. Oh, we'll start here. We'll pick up on this slide because there's a few to fill in. So have a good weekend. Stay dry. No snow. It's looking like it might snow. The cold front come down.